Before we start our next topic, I would like to correct a small tutorial problem that we did last time. If you remember, there was a function t to the power half for which we are computing the Laplace transform. So, gamma n is this. Now, gamma n is basically n minus 1 gamma n minus 1. So, here it should be gamma 3 by 2, which is half, there was a slip here, it should be n minus 1 gamma n minus 1. So, it should be half gamma half. So, please make this correction, I am extremely sorry, it will be half root pi s to the power 3 by 2. Okay. Today, we shall be starting frequency response of systems. Frequency response of various types of networks. What do you mean by frequency response? When we excite a system by, say, we have a sinusoidal input Vm sin omega t applied to a network whose impedance function is Zs, all right, in the Laplace domain. In the time domain, we are applying a function Vm sin omega t. So, in the Laplace domain, this will appear as Vm into omega by a squared plus omega squared. So, this is our input function, Zs is the impedance function. What will be the output? Now, in this we may treat the current as the output. Okay. So, Is will get as Vs by Zs. We can write Ys into Zs. So, for any system we define Ys into Vs, thank you, Ys into Vs. So, if Vs is the input and Is is the output, 1 by Zs is the multiplier, we call it a transfer function. Okay. So, input multiplied by a transfer function is the output. In this particular case, it happens to be 1 by Zs. The transfer function depends on how you define the input and the output. For a 2-port network, we may define output as V2 and input as V1. So, V2s by V1s will be the transfer function. Somebody may be interested in the current that is flowing under open circuit condition or maybe under short circuit condition. So, it is not necessary that it should be always V2 by V1, the transfer function depends on how you define the output. Okay. Now, we will evaluate right from the start what will be the output in the time domain and at steady state what will be the response like. So, let us take a simple example. Sorry. We have a resistance and an inductance. We may be interested in finding the current I t when we are exciting this by a voltage V t. Suppose V t is given as, let us take an example, 50 sin 10 t. R is say 10 ohms, inductance is 1 Henry. What will be the current I t? So, I will replace this by the transformed equivalent which will be R plus SL which is 10 plus S, and this side it is 50 into omega is 10 divided by S squared plus 10 squared, that is 100. Is that all right? So, what will be IS? It will be 500 by S squared plus 100 into 1 by ZS, that is S plus 10. If I make partial fractions, I can write this as A by S plus 10 plus Bs plus C by S squared plus 100. So, multiply by S plus 10, then put S equal to minus 10. So, that gives me 500 minus 10 squared is 100 plus 100 200. Is that all right? So, it will be 5 by 2. Okay. If I subtract 5 by 2 S plus 10 by S plus 10 from the original one, I will straight away get Bs plus C. Is it not? Otherwise, by residue calculations, by any method you can calculate S square plus 100 into S plus 10 minus 5 by 2 into S plus 10. Is that all right? So, that comes out to be 2 into S square plus 100 into S plus 10 divided by multiplied by here, that is 500. So, it will be 1000 minus 5 into how much? S square plus 100. Okay. Is that all right? So, that gives me 1000 minus 5 S squared minus 500. So, 500 minus 5 S squared divided by 2 into S squared plus 100 into S plus 10. So, that gives me, if I take 5 common, it will be 10 minus S into 10 plus S divided by 2 into S squared plus 100 into S plus 10. So, that gives me 5 into 10 minus S. So, 5 by 2 minus 5 by 2 into S minus 10 divided by S squared plus 100. Is that all right? 10 plus S goes. So, it is like this. Therefore, the given function IS is 5 by 2 S plus 10 minus 5 by 2 into S by S squared plus 100 minus and minus plus 5 by 2 into 10 by S squared plus 100. Is that all right? So, what will be IT? It is 5 by 2 a to the power minus 10 t minus 5 by 2 S by S squared plus 100, inverse will be cosine 10 t plus 5 by 2, this one will be sine of 10 t. So, 5 by 2 e to the power minus 10 t minus 5 by 2 sine, I can write plus sine 10 t, okay, minus 45 degrees. Cosine 10 t, sine 10 t, both are having the amplitude 5 by 2. So, it will be 45 degrees, one is plus, the other one is minus. Anything else? there will be a magnitude will be root 2 times this, is it not? So, 5 by 2 into root 2. So, I can put 5 by root 2, is that all right? Now, as time passes, this will be dying down. The response is, the current is having a component which is dying down like this, plus another component which is 5 by root 2 sin 10 t minus 45 degrees. So, like this. Okay. So, the sum total of this will be the total response. This component will be vanishing after some time, it will die down. So, if you are interested only in the steady state value, then it is this component which will be continuing. So, when we say steady state response of the system, when you switch on a circuit, this part will be vanishing within a few seconds, maybe milliseconds, depends on the time constants involved. Okay. So, most of the time we are interested only in the steady value. What is that steady value? So, it is this quantity. Now, when we say we are interested in the frequency response, means basically we are interested in the steady state response of the system. As the frequency changes, this amplitude will be modified, all right, and also the phase, this 45 degrees will not remain 45 degrees. If I have a frequency instead of 10 radians per second, if I go for 20 or 30 radians per second, both this magnitude and this phase will be affected. So, how is this and this, how are these two quantities going to change with frequency? If you can predict that, then we need not go through all these computations. Okay. So, you can see for yourself, for this example, our function was, the transfer function was 1 by s plus 10, that was 1 by z s, is it not? So, we have put V s as the input, 1 by s plus 10 as the transfer function, and I s was the output. So, if you are interested in knowing the steady value, the steady state value of the current, then just put s equal to, let us see, if I put s equal to j 10, means j omega, where omega is the frequency, in this case it was 10 t, sin 10 t, so omega is 10. If I put s equal to j omega, then what will be this equal to? 1 by 10 plus j 10, which means 1 by 10 root 2 and an angle of 45 degrees. Is that all right? That means 1 by 10 root 2 minus 45 degrees. So, now you see what was our input voltage? 50 sin 10 t, this was our input. Here what is the gain? We call this term gain, that is the magnitude of G s at s equal to j omega. Okay. This is our G s and we are evaluating G s at s equal to j omega, whatever be that omega. So, this will be having a magnitude and a phase. What is the magnitude? 1 by 10 root 2. What is the phase? Minus 45 degrees at this frequency omega equal to 10. So, 50 was the amplitude of the input that gets multiplied by that magnitude of g j omega. Is that all right? So, it will be 50 1 by 10 root 2. This will be the amplitude of the output, sin 10 t the same frequency sin 10 t with a phase shift of theta, here theta is minus 45 degrees. This will be the output. So, the current you can straight away write from the given input voltage, provided you know the value of this g and theta from the given function, all right. So, our primary task therefore will be to evaluate Gs at different frequencies s equal to j omega. Evaluate the magnitude and the phase. Then for any input I can always calculate current without going through this entire exercise of Laplace transforming, taking inverse and so on. Once you know Gs, is that all right? So, frequency response means calculation of g j omega and theta. So, we will try to find out a method of approximately computing these two quantities g and theta with respect to frequency, how it varies, how g varies with frequency. Let us see that. Now, since we will be varying the frequency over a wide range, we take the frequency scale in a logarithmic scale. So, in logarithmic scale you do not have a 0, 0 means log of 0 is minus infinity. So, you can always have, say we can choose arbitrarily any scale 1, 10, then the next equivalent length will represent a decade 10 to 100, next equivalent length will be 100 to 1000 and so on. So, how much will be this? This is 1 decade. So, how much will be this? 0.1. Had I had 1 starting from here, then 1, 0.1, 0.01. So, you can never approach 0, you can go to 0.1, 0.01, 0.001 depending on the scale that you want to choose, the range that you want to choose. You can have 3 decades, 4 decades, 5 decades. In the market you will get, you can get the graph sheets, semi-log graph sheets with 4 decades or 5 decades or 6 decades, or you can prepare one if you want. So, this will be depending on the range of the frequency that you want to work on. This side, instead of taking the gain as it is, gain we define by, say in a 2-port network we write in terms of say voltage, ratio of voltages or currents and so on. We are quite often interested in knowing the power gain. How do you define power gain then? Over the same resistance, say across the same resistance, if I apply a voltage V2 or V1, how much will be the ratio of the power? It will be V2 square by R and V1 square by R. So, if I take the ratio, it will be V2 squared by V1 squared, that will be the power gain. Okay. If G is the voltage gain, then power gain will be G squared. Okay. We are only interested in the magnitude at this time. Now, human perception of power gain will be always in a logarithmic scale. When you see an image or when you hear a sound, if the energy of the sound or the light is just doubled, if you just double the intensity, the perceived intensity will be log of 2 in some logarithmic scale. That means, if I change the brightness, if I give the input energy to the light double the previous value, then I will not be receiving, I will not be feeling that the light has been doubled, the intensity has been doubled, it will be in a logarithmic scale. Similarly, when you hear a sound, if the energy of the sound has been doubled, then I will be receiving it as log of 2. The perceived intensity will be varying logarithmically. Okay. So, it is better to define a new gain function which will be log of the original gain function P2 by P1. We choose a base 10. Base is not so much important, we could have selected the natural log also. That will be giving just a constant. How much is that constant? Log of 10 to the base e 2.303. Okay. So, log of say V2 by V1 squared, that means basically twice log of original g. Okay. We call this unit as a bell. Okay. Now, in some countries, the currencies are of such a denomination, people get salaries in thousands of rupees, say 50,000. An average man getting 50,000 rupees salary will be somewhat unthinkable, no. But with 50,000 rupees, if he goes to the market, he will be hardly able to buy anything. So, depends on the strength of the currency. In Japan for example, you have yen, or in Italy you have lira. People get say 50,000 lira, they go to the market and buy something. You do not go with say paise. I cannot say my salary is 50,000 paise, is not. So, or 5 lakhs paise, we have a little relatively harder currency. So, instead of 100 rupees, you may also have 10,000 paisa. I am going to the market with 10,000 paisa, is it not. So, or sometimes if you have the reverse situation, that is I get salaries in lakhs of rupees. So, maybe 0.05 lakhs, all right, or 0.005 lakhs, with that rupee I will go to the market. So, that will be too small, is it not. So, the units for any such quantity will have to be something which will be very easily which can be handled very easily. So, bell is such a unit that you will be getting a gain of say 0.03, 0.04 or maybe 0.5 like that. So, we multiplied by 10, okay, and define a decibel as the unit for gain. That is, in terms of rupees you are defining in terms of paise, the cost of anything you are defining in terms of paise. So, you multiply by 100. Similarly, in terms of decibel it will be 2 into 10 into log g, is it not. 2 rupees means if I want to write in terms of paise it will be 200 paise. Similarly, 2 log g, so much decibel will be 20 log of g, so much decibel. So, 20 log of g is most commonly used unit for gain in the logarithmic scale. Okay. So, we will be interested in finding the variation of this quantity 20 log of g given a function gs, variation with respect to frequency. So, let us take one simple example, gs equal to say 10 by s plus 10. Okay. What will be the frequency response for this? That means, how is this quantity 20 log of g varying with frequency omega? How is it varying? If I keep on changing s, the value of s, so this will be 10 by 10 plus j omega. Okay. 10 by 10 plus j omega, I might as well write this as 10 by 10 into 1 plus j omega by 10. Okay. So, that gives me 1 by 1 plus j omega by 10. What will be the magnitude? G magnitude will be 1 by 1 plus omega squared by 100. Okay. Now, when omega is very, very small, that means omega is much less than 10, G will be tending to how much? This is negligible, so it will be 1. So, 20 log of G will be log of 1 is 0. So, it will be approximately equal to 0 dB, okay, when omega is much less than 10. When omega is much greater than 10, if I call omega by 100, omega by 10 as x, it is basically 1 plus x squared, okay, under root. So, this x squared will be dominating over this term. So, I can approximate this to 1 by omega, 1 by root over of omega squared by 10. So, omega by 10, okay. And how much is this going to be? This will be 10 by omega, okay. So, when omega is equal to 10, how much is it? 1. So, I will choose omega equal to, this is omega, okay, let me take, let me draw it here fresh. Let this be 1, this be 10, this be 100 and so on. When omega equal to 10, omega by 10 is equal to 10 by omega is 1. So, log of 1 is 0. If I increase the frequency tenfold, say you take any quantity log of omega, and at omega equal to omega 1, say log of omega 1, and if I increase the frequency tenfold at some other frequency omega 2 equal to 10 times omega 1, what will be the value? Log of 10 omega 1. How much is this? If I increase the frequency 10 times from any value, omega 1 is say 5, then from 5 to 50 if I go, then this will be log of 10 plus log of omega 1. That means, compared to the previous value log of omega 1, I am getting an additional term of log of 10, and log of 10 is 1. So, if I multiply by the 20 log of G, so it will be 20 into 1. So, I get an additional 20 dB increase for a function log of omega 1. Now, here omega is in the denominator. If I take log, it will be minus log of omega. Okay. So, minus log of omega will have minus 20 dB additional term for every decade increase in the frequency, is it not? So, whatever be the value at 10, omega equal to 10, omega equal to 100 will give me an additional value of 20 dB. It could have been any frequency, I can take say 12, then at 120, that is 10 times that frequency, whatever was the value, I will go down by 20 dB, that will be the new value of the function at 120. So, you take any frequency and 10 times that frequency, the jump will be by 20 dB. So, if I draw a line at omega equal to 10, in this example it was 1. So, at 100 it will be 20 dB, at 1000 it will be 40 dB, another additional 20 dB. So, at every decade, all right, if I increase the frequency tenfold, I will always get a 20 dB additional term. here it will be in the negative region. So, I can join these points 20 dB at 100, 40 dB at 1000 and so on by a line. So, it will be approaching either this one or this one as the frequency increases. So, these are the two asymptotes corresponding to a function 1 by s plus 10. Okay. It is 10 by s plus 10. Okay. So, the actual frequency response may be going close to this, it will be meeting this asymptotically, this one also asymptotically. So, the actual curve will be somewhat like this. Okay. Let us have another function 1 by s plus 5 into s plus 20, say 100 divided by s plus 5 into s plus 20. Okay. Let it be 200 divided by s plus 5 into s plus 20. I can always write this as 200, I can take 5 outside, 20 outside, and it will be 1 plus s by 5 into 1 plus s by 20. Is that all right? I can write like this. So, that gives me 2 into 2 by 1 plus s by 5 into 1 plus s by 20. So, what will be the logarithmic plot for this function? If I take 20 log of g, it will be 20 log of 2 minus 20 log of 1 by root over of 1 plus omega squared by 25 minus 20 log of 1 by root over of 1 plus omega squared by 400. Do you agree? So, 20 log of 2 is 0.3. So, 0.3 into 20, 6 dB. So, let us take each of these components separately, plot them and then add them together, that will be the resultant plot. So, first component is 6 dB, that remains constant. Okay. This is 6 dB. All right. Next, 20 log of, say the function 1 plus s by 5. What is that critical frequency where this component will be dominating over the other component? It is at omega equal to 5, is it not? So, omega equal to 5 is one critical frequency, from where I can straight away show a 20 dB per decade slope. So, the function here 20 log of 1 by root over of 1 plus omega square by 25 will be an asymptote like this. Okay. At omega equal to 20, similarly there will be another 20 dB per decade line. So, a curve like this will come. Is it all right? Now, we are not really interested in the exact plot, we will be approximating it. that is good enough. So, what will be the resultant of these three components? One is a constant here, then at this point there is a break 20 dB per decade slope, and at this point there is further 20 dB fall. So, there will be another line of 40 dB per decade. So, this will be the resultant one, 6 dB constant line, then at omega equal to 5 it will be falling at the rate of 20 dB per decade, then here from omega equal to 20 onward it will be 40 dB per decade. Is that all right? And then the actual plot will be somewhat like this. We are not interested in the exact plot. So, this is 20 dB per decade, this will be 40 dB per decade. Okay. Now, instead of increasing the frequency tenfold in an expression like log of omega, if I increase the frequency tenfold, then I get an additional term of 20 log of 10, is it not, plus 20 log of omega. If I increase the frequency twofold, that is if I just double the frequency, then what will be the additional term? 20 log of 2. I have just doubled the frequency. So, 20 log of 2 will be the additional term. How much is that? 6 dB. So, 20 dB per decade is same as 6 dB per octave. This octave is different from the octave that we use in music systems, all right, in sound. Octave here in electrical engineering, when we talk about frequency response, octave means double the frequency, that is the second harmonic. So, for any omega, if I double the frequency, there will be an increment or decrement of 6 dB. So, sometimes these slopes are written in many books, you will find 6 dB per octave. It is as good as 20 dB per decade. Now, if you are having a factor of, say, instead of 1 by s plus 10, if you get a factor 1 by s plus 10 whole squared, then what will be the rate of fall? At that same frequency omega equal to 5 or omega equal to 10 or omega equal to 20, the line will be falling at double the rate. So, it will be 40 dB per decade. Okay. If you have a function in the numerator, a factor in the numerator, say g s equal to s plus 10 divided by s plus 1 into s plus 40, what will be the plot? I can take 10 common, 1 plus s by 10, s plus 1 into 1 plus s by 40 and 40 common. So, 1 by 4 into this. If I take log 20 log of g will be 20 log of 1 by 4, okay, plus 20 log of the numerator term root over of 1 plus omega squared by 100 minus 20 log of root over of 1 plus omega squared minus 20 log of, I am not writing to the base 10 every time, it is understood we are working with the base 10, 1 plus omega squared by 1600. Okay. Once again you take term by term these quantities, 20 log of 1 by 4, how much is it? Log of 1 by 4 means minus log of 4, log of 4 is 0.6. So, 0.6 into 20. So, it will be minus 12 dB, this will be minus 12 dB plus the other terms. So, the plot will be, now you see here we are having a numerator part which is giving me a plus term, here, and the denominators are giving me 2 minus terms. So, you have minus 12 dB. So, if this is 0, if this is minus 12, this is the first part. The second part is at omega equal to 10, omega equal to say this is 1, this is 0 dB, this is say 1, this is say 10, this is say 40. They are not really to the scale, 40 may be somewhere here. Okay. So, at omega equal to 10, you are having a numerator function, that means it will be increasing. 20 dB per decade line will be like this, and at omega equal to 1 it is falling like this, 20 dB per decade. At 40 again it is falling like this. So, what is the net sum? It is this plus this plus this plus this. So, minus 12 dB, the net value say in this range is minus 12. So, it will be following this way, minus 12. Then at omega equal to 1, there is a slope of 20 dB per decade, the fall starts. So, it will start falling at 20 dB per decade. That means, a parallel line I will draw 20 dB per decade like this. At omega equal to 10, there is an increment of 20 dB per decade. So, this will be offset by 20 dB per decade increase. So, it will be finally horizontal, no increase or decrease. This was falling at this rate, this is increasing at the same rate. So, it will be remaining constant at that value. At 40 again it will start falling. So, this is 20 dB per decade, 0 dB per decade, again 20 dB per decade. This will be the gain plot like. Is that all right? Yes. 20 log of 2.
This 2 becomes plus 20 minus this minus.
This problem you mean?
No, no, sir. So the previous one.
First example was
This
20 log 2 plus
this one.
this one, but the previous slide. Previous slide you shown the expression 20 log 2 mod g. That is
plus
this 2.
20 log this one
This becomes plus 20 log. Right.
plus 20 log.
Plus.
Huh. Thank you very much. Because all of them are actually,
This also
thank you very much. These are plus signs. Sorry, there is a small slip earlier. I was having this in mind that the denominator will come with a negative sign, but instead of converting them I put negative signs. It will be plus, this will also be plus, automatically when they come in the numerator it will be minus. Thank you very much. So, this is the final gain plot. Sometimes you are having a function like 1 by a squared plus a how much should I write? Okay, say a squared plus this is 100 plus 10 maybe 5s plus 100. You cannot factorize this into real roots, b square is less than 4ac, all right. So, there will be complex roots. You write this in the form of s squared plus twice zeta omega n s plus omega n squared. Okay. Omega n is therefore 10 and zeta will be 5 by twice omega n is it not? Means 5 by 20. So, that is 0.25. For such functions, what will be the sketch like? When omega is very small, when omega is very small, it will be 1 by omega n squared. Okay. S is j omega when we are evaluating this entire function for s equal to j omega, and omega is very small. So, this term will be tending to 0, this term will be tending to 0 because there is a multiplier s. So, it will be 1 by omega n square. So, this will be 20 log of omega n squared with a negative sign, because it is 1 by whatever be that value depending on omega n squared. In this particular case omega n square is 100. So, 20 log of 100. So, log of 100 is how much? 2. So, minus 40. So, it will be minus 40. So, if I take this as the 0 dB line, so this is minus 40. Okay. So, this will be the value corresponding to omega 0. So, this will be the asymptote line. When omega n is very large, this will be tending to 1 by a squared, alright. That means 1 by omega squared. It will be tending to this. When we take two extreme values, s tending to 0 and s tending to infinity, s equal to j omega, omega tending to infinity, then you get the two limits. That means the asymptotes are estimated from this. The function will be approaching either this value or that value. So, 1 by omega squared, if I take 20 log of that, how much is it? Minus 40 log omega. Is that all right? For 1 by omega square, if I write 20 log of 1 by omega square, that will be minus 40 log omega. So, how much will be the slope? 40 dB per decade. Is that all right? So, it will be from 10 onward at omega n is equal to omega equal to 10, at omega equal to 10 or close to 10, we will see. So, 40 dB per decade will be the slope of this. Somewhere in between, when omega equal to omega n, omega equal to 10, in this particular example omega equal to 10, how much is this? Minus 100, plus 100 and minus 100 terms will get cancelled. So, 1 by s squared plus 5s plus 100 will tend to, at s equal to j10, j10 means I am putting omega n value, it will be this and this will cancel, it will be 1 by 5 into 10. So, that is 1 by 50. Okay. So, it will be log of 1 by 50 is how much? So, 20 log of 1 by 50, how much is it? So, I can always write 20 log of 50 negative sign. So, minus 20, how much is log of 50? Log of 5 is 0.7, log of 10 is 1. So, 1.7 into 20, 34. Is that all right? So, 34 dB minus. So, earlier it was 40, now it will be minus 34 dB. So, it will be going like this, going up to 34 and then falling like this. Is that all right? It will be falling like this. Depending on the value of zeta, this will be either very peaky or very flat. Now, let us see how this changes with zeta. If s squared plus 5s plus 100, if I reduce this, make it approximately equal to 0, then what happens? 1 by s squared plus 100, this term is missing, zeta is made 0, it will be 1 by s squared plus 100, and at s equal to j 10. So, how much is g j 10 tending to infinity, is that all right? So, the magnitude, if I take the log at omega equal to 10, it will be approaching that 40 dB per decade line. Okay. Slope will be finally 40 dB per decade, it will be tending to infinity and then again coming from there. So, zeta, as I keep on increasing zeta, this will keep on falling like this. Okay. So, this is zeta increasing, a simple way of giving the symbols. This is the direction of the curve tends like this as zeta increases. When zeta is more than say how much? Okay, when zeta is equal to 1, then it will be 1 by s squared plus twice omega n s plus omega n squared. That means 1 by s plus omega n whole squared. There are two real roots, two equal real roots. So, at omega n, straight away there will be a 40 dB per decade fall, all right. Is that okay? At omega n, that means two roots are coming, if you remember, for different values of zeta, if you calculate the roots of this quadratic, okay, we will take it up in the next class, how the roots travel, how the roots are changing. For different values of zeta, the complex pair of roots will be moving like this, and then this is the time when they will become equal. If you increase zeta beyond this, the roots will be real, but they are separated now. Two distinct roots you will be getting. Okay. So, we will take it up in the next class, and then we will see how to make the phase plot from the gain plot. Okay, friends, we will continue with some more examples on Bode plot. Last time we were discussing about the plot for a function of this form, 1 by s squared plus 5s plus 100, that is twice zeta omega n s plus omega n squared. For different values of for different values of zeta, you will find this peak value occurs at a shifted value, shifted point here. That means the peak gradually shifts to the left at a frequency omega d, which is equal to omega n into root over of 1 minus zeta square. Omega d equal to omega n into 1 minus zeta squared. When zeta is small, we can approximate this to omega n. Now, we come to a frequency plot, phase plot. Let us once again compute the phase for each of these factors, like say 1 by s plus 10, 1 by s plus 20 and so on. If you have a factor like this, what will be the corresponding phase? if I put s equal to j omega, so omega equal to 1, omega equal to 10, omega equal to say 5 and so on. When it is s plus 10, that means 1 by j omega plus 10. When we take omega equal to 1, omega equal to 1, how much is this? 1 by 10 plus j. Okay. So, 10 plus j, how much is the angle? Tan inverse 1 by 10. Tan inverse 1 by 10, that is tan inverse of 0.1. Okay. So, that gives me tan inverse of 0.1 with a negative sign. So, that will be minus, how much is it? Tan inverse 0.1 is 0.1, tan theta is equal to theta when theta is small. So, 0.1 radian, approximately 6 degrees. 57 degrees will become 1 radian. So, 0.1 radian means 5.7 degrees, approximately 6 degrees. Okay. If I take 10 times this frequency, that is when omega is 100, then it will be 10 plus 100 j, all right. So, how much is tan inverse 10? Tan inverse 0.1 is 0.6. So, just 1 by 0.1, that means 90 minus 6 degrees will be 84 degrees, okay. It will be 20 dB per decade, minus 20 dB per decade, and then again at 50 minus 20 dB per decade, all right. So, what is the resultant of these three? Resultant will be, if I am permitted to draw by a dotted line like this, it will be actually this line, and then at 9, okay, at 9 this will be minus 20. So, it will be plus 20 dB per decade, it will go on like this, and at 50 it will become horizontal. So, the net function will look like 40 dB, 20 dB and then horizontal one, and then depending on the constant 20 log of 1 by 50, it will be shifted up or down depending on its magnitude. Here it is 1 by 50, so it will be negative. So, it will be brought down by this factor 20 log of 50. Is that all right? So, we will stop here for today. We will take some examples in the next class. Thank you very much.